of pair chain. I'm not feeling super well today, so hopefully I can articulate my points clearly, but I might just cut the video short. uh, doesn't matter. Okay, so let's go ahead and get right into this problem. So maximum length of pair chain. You're given an array of n pairs, where pairs I equals left I, right I, where left I is less than right I. Okay, so you can think of these pairs as like a set of tasks, right? Where the task starts at left eye and it ends at right eye, right? So for task I, this task I begins at left eye and it ends at right eye. And of course, the time that the task begins has to be less than the time that the task ends, right? Something has to start before it ends. So that's one way of looking at this. A pair P2 follows pair P1 if B is less than C. And a chain of pairs can be formed in this fashion. Okay. So A, B has to be if B is less than C, right? So the time that this task ends, right? So it ends at time B, it has to be less than the time that this task starts, right? Which it starts at C, right? So task 2 starts at time C, it ends at time D. And task 1 starts at time A and it ends in time B, right? This pair chain could be created because if, right, the time that P1 ends, which is time B, is less than the time that P2 starts, which is time C. Return the length of the longest chain which can be formed. You do not need to use up all the given intervals. You can select pairs in any order. Okay, so this problem is very like I'm trying to remember which problem this reminds me of because it does remind me of another problem. But essentially, there's this problem where you're trying to find the maximum the longest subsequence, the longest increasing subsequence. I would say that's what this reminds me of, right? Because there's this idea of a longest increasing subsequence where, just to kind of iterate through the problem quickly, right? If you have like 1, 5, 6, 2, 4, 8, 10, right? The longest subsequence would be saying, the longest increasing subsequence would be saying, how do I find a subsequence, right? So members of this thing in a row such that, it's increasing, right? So I can go from 1 to 2 to 4 to 8 to 10, right? That has length 4. I could do 5, 6, 8, 10. That also has length 4. I could do 2, 4, 8, 10. That has length 4. No. So 1, 2, 4, 8, 10 has length 5. So that would be the longest subsequence, right? So I go 1, 2, 4, 8, 10. Now the reason why this problem reminds me of that is because, there is a certain order to these tasks, right? Like if we were to draw out these tasks, right, it's kind of like the longest increasing subsequences, right? Because the times have to be in some sort of order, right? Because if I think of these things as tasks, these pairs, right, there can't be any overlapping pair. So I could choose 1 and 2 and then 3 and 4, right? I can't choose 1, 2, and 2, 3, right? Because they can't have overlap, right? It has to be less than, C has to be greater than B, right? So this has to be greater than the previous value's end time, right? So this is really just that problem, right? Like trying to find the longest schedule that you can take, right? What are the maximum number of classes that you can take, right? What are the maximum number of tasks that you can do? And that's very similar to this idea of a longest subsequence idea, right? And in order to solve this problem, there's an n-squared solution, dynamic programming solution, right? Where you look at each node and you look at what's to its left and see what it can connect to, right? So when I look at 5, I know it can connect to 1, and it can, when I look at 6, it can connect to 5 and 6. When I look at 2, it can connect to 1. When I look at 4, it can connect to 2, and it can connect to 1. And when I look at 8, it can connect to everything. Right, everything can connect to 8. Right, so you draw the system out, and then you just try to find the longest path in the system. So that takes n squared time. So I think that there's intuitively the same argument that can be made With pairs, if you think of them as terms of like a longest increasing subsequence, if you were to sort this, right? So if you sorted this, if you look at this task, you could say, okay, what's the longest chain I can attach this task to, right? This pair. Sorry, I keep using those terms interchangeably, right? So what's the longest pair that I can attach this? What's the longest pair chain that I can attach this pair to, right? What's the longest pair chain that I can attach this pair to, right? So we can build them forward. And as long as they're in order, right, then we can ensure that whatever chain I attach it to has already been computed. So in this example, right, the longest paired chain I can attach 7, 8 to is actually 4, 5, right? So you want to make sure that you compute 4, 5 before you compute 7, 8, right? If you think of this in terms of dynamic programming, right, when we solve this problem, we can figure out what the best chain to attach 8 to is because we've already solved for all the things that are less than 8, right? So we've already solved for everything that comes to the left of 8, so we can figure out which chain it's supposed to attach to. That's the general idea, right? So when we look at this problem, we would want to sort it in terms of end time first, right? So I'll just solve this problem quickly, right? So if we sorted pairs, we'd have in terms of end time, and then y in terms of end time. What we can do is we know that everything to the left of us, right? Like if we look at any node, we know that anything to the left has an end time before my end time, right? It's possible that my start time is before their end time, right? Because like imagine you had a task like this. So you had one task. So I'm drawing these lines out to say like the schedule. So this is a length 2 schedule. And then say there was something else that ended after, but it also started before. Right, so in this case, this one would come before this one, right? This node would come before this node, but, you know, they can't both be used, right? Because this one starts before this one. So it's a little bit of a weird situation. So how do you know how do you figure out the chain that you can attach a task to, right? So if we had, if we looked at, I can attach, so if we look at 1, 2, right, I'm trying to think about how to do this. So if we had 1, 2, and 4, 5, and 7, 8, if we drew these as nodes, right, where we're trying to find the longest increasing subsequence, well, all of these have length 1, right? Like I can choose any of these and it'll be a length 1 chain. But how do I know if you can attach yourself to a previous chain? Well, 1, 2 can't attach to anything, right? Because there's nothing to its left. 4, 5. Can 1, 2 then go to 4, 5? Yes. Why? Because, well, it's really just the fact that I know that I end after you because I come after you, right? Because I sorted this system. So since the system is sorted, I know that 4, 5 ends after any node to its left ends. So as long as my start time is after your end time, right? Does it have to be? No. So as long as, yeah, that's what I'm sorry, I'm proving myself something I just stated. But as long as my start time is after your end time, that means I can attach to you, right? So when I look at 4, 5, I say, okay, 4, you start after the previous one ends. And since you start before the previous one ends, you know, you definitely end after it, right? So then I know I can create a link here. And then when I look at 7, 8, right, I look at anybody to my left, and as long as everyone to my left ends before me, so I know that there's no confliction in that respect, so I need to check if they end before I start, right? So I start at 7, this starts at 5, so then therefore I can connect it. This starts at 2, and I mean, this ends at 2 and I start at 7, so I can definitely connect this too, right? So here's all the links in the system. So then now all we need to do is figure out what the longest length path is in the system using dynamic programming. And the idea would be to just, you know, find the longest length path here and save that information, right? So this would say, okay, the longest length path here is 1, right? And then this system would say, okay, I can either consider myself or the neighbors that go into me. I have a neighbor of length 1 that goes into me, so that means I have length 2 path. right? And then I'd process this next node. This next node could say, okay, I can either process myself, which is 1. I can consider this path, which would give me 1, which would give me a total link 2. Or I can consider this path, which has link 2, which could give me a total link 3, right? So it would select this path, which is the basic dynamic programming aspect, right? So let's go ahead and code up that solution pretty quickly. So first thing we want to do is we want to sort pairs. Whoa, what the hell? We want to sort pairs in terms of the end time, right? The time that the task ends, right? So we'd sort it. We'd say, okay, the key is, well, we take lambda, we look at each pair, and then we'd sort it based on the last value in the system. And then we need to have a dynamic programming array, which saves information about the longest path that we have found up to a node. So this would be length of pairs. And then we would just look at each index and each pair in pairs. Right now, since pairs is sorted, we can just process all the indexes to our left, right? So we would say, well, the D at this index, we'll do SE equals pair, just to say, okay, this is the start time of this element and the end time of this element, right? So I'm looking at each element, I'm looking at its start time and its end time, 4 and 5, and then I'm going to look at everything to the left, right? Because if index is here, then I can look at everything to the left of index, right? Okay, so this is very very much so like longest increasing subsequence. So I'd say this is the max of, well, I'd add in the max of, because I'm going to get my own length path, which is length 1, plus the length of the chain that I can connect to, right? So D of J, we'll call it JDX, I guess. For JDX in range IDX, right? I can check all the nodes to my left because they all have an end time before my end time, as long as they start, or as long as they end before I start. So as long as they end, so if this thing ends, it has to end before I start. And then it might be the case that nothing meets that situation, so you know, I have no neighbors that go into me, so the default is 0. And then at the end, you just return the maximum path from D. Right, because this will have the length of each chain at each node, so whatever the max chain is, that'll give us the answer there. Okay. Because I use default, I can't just leave it without a parenthesis or square bracket. Okay. So this is one solution. This is the solution that I determined just instantly. The runtime is, so we have time and we have space, right? The time complexity is, well, we have to sort the whole system. So if we said that n equals the length of pairs, right? So we have to sort the whole system. So that's going to take n log n time. And then we have to look at each pair of nodes. That takes n time. And then for each pair in the system, we have to look at everything that comes before it to make a decision about the best chain to connect ourselves to. So that's going to take another n time. So for each n operations, we have to do n operations. So that's going to take n squared time, you know, plus don't forget about n log n. It's going to get, you know, shadowed by this because this is going to grow much faster. And then for space, well, this technically would take n space to create a new array, but you can use like in place heap sort. So this could actually be constant space, right? So we'll just say, for the sake of argument, that this is constant. And if in an interview they said, no, it's not constant the way you did it, just say, okay, there is a way of doing it in constant time. There's in place heap sort that also takes n log n time, but it uses constant memory. So if you really want this to be constant, it can be. And if they ask you to do it, say, I don't remember how to do it. I haven't been in university for a while. And then for space, right, so we have O of n. So the actual n space comes from this, right, because we have to keep information about the longest chain at any node. So this is O of n. So this is pretty good, right? It meets the conditions, but there's actually a faster solution, and we're going to go through that now. So the thing is that if you sort, right, so let's imagine that we sorted pairs, and we have a system of A, B, C, D, E, F. Okay. Now this system is sorted. Okay. So I'm just doing a very small example, but a general example to prove a point about who the best person is to pick or whatever. Well, okay, so we know since this is sorted that B is less than D, which is less than F, right? I guess they could technically be the same, right? So we know that this is true, right? Because we're saying that this, imagine this was pairs and we've already sorted it. So we know it's true that B is less than D, which is less than F, right? Because it's sorted by n times. So B is less than D, B is less than or equal to D, which is less than or equal to F, right? We know that to be true because we sorted this system, right? We're still going to do that. We're still going to sort pairs, all right? What that also means, though, is, well, since A comes first, right? And a task has to start before it ends. So if A is before B, right? Because A starts and B is when it ends, and B is less than D is less than F. Well, then A also has to be less than or equal to B, less than or equal to D, less than or equal to F, right? That has to be true, right? Because this thing ends before this thing ends, and this thing ends before this thing ends. But it has to start before the first thing ends, right? The first thing has to start before the first thing ends. So this is also less than, right? So it's only going to benefit you to select this one, right? Like it's the best to select this one. All right, like it's optimal to select this first node, right? Always, right? Because it starts before everything else. It starts before the first thing ends, and the first thing ends before everything else ends. So it's like to the most, it's most to the left, right? And since, sorry, I'm really trying to walk through how this works. This is a greedy approach. So like greedy proofs can always be some of the most difficult to understand and even explain. So this thing starts first. So this is definitely true. So why is choosing this the best? Well, if C can either start before A or can start after A, right? Like if you look at A and B, so we know that A comes before B, right? And we know that D ends after B, right? Because B is less than D is less than F. So D either starts after, is either after, so C is either after A, right? Well, so if C starts after A, well, then it's definitely better to choose AB, right? Because you're shifting it more to the left, right? Because this can only give you a better solution because I'm not overreaching, right? D can make my solution only worse because I'm going further in time, right? Since I'm going further in time here, right? If there's another task that's here, right? I'm not going to be able to get it if I choose D, right? But I will be able to get it if I choose AB. So it's better to just choose this one anyways, right? Because there's not going to be a task over here, right? There's not a task that I'm missing out on in the other direction, right? There's no task that I'm missing out on the other direction. Because if that were the case, then the first thing wouldn't be this, it would be this, right? If it was the case that there was a task to my left, there are no tasks to my left because this is the first task, right? A is the first thing. AB is the first task that completes. So there's nothing to the left. So I don't need to worry about that. So that only means that it's better to choose AB because it's not going to conflict with anything. CD can only conflict with something. So I should always choose the task that ends first, right? I should choose the task that ends first because D ends later. So D ending later can conflict with something in the future. So since I end first, I'm the best person to be with in this picture. And then what if C came before D? I mean, what if C was before A? So what if it was like this? We might say, okay, well then is it better? Well, we're not choosing length, right? We don't care about the length of the task. We just care about the number that we can chain together. So the fact that C starts before A doesn't change the fact that, there's no task up here and D can only conflict with future tasks. So it's always going to be better to choose AB, right? So then how do you choose subsequent tasks? Well, if a subsequent task doesn't conflict with the current task and we're doing it in order of end time, right? So for a subsequent task to not mess with a current task, what does that mean? That means that the next task's start time has to be later than my end time, right? So we know that choosing the first one is optimal. How do we know if choosing a subsequent one is optimal? Well, if a subsequent one is optimal, because we're trying to just always choose the closest end time, right? Because as we showed with the previous example before I erased this like an idiot, right? Something ending later just spills into the future. And since it spills into the future, it could conflict with future events. So we should always be trying to pick events that don't spill into the future, that keep us as close as possible to where we're at, so that in future events can be chosen, because we've already looked at everything to our left, right? Because we don't want events that spill into the right. We don't care if events spill into the left, because we've already found out what's optimal when looking at things to the left, right? So if the next task can be chosen, which means that its start time is after our end time, then its end time, the task that we're going to choose, its end time is optimal, right? Because we have this system sorted. So its end time can only be less than or equal to future end times, right? D can only be less than or equal to F. So if we can choose this thing, we might as well choose it, because it's not going to spill into the future. So that's the general idea of this system. So if we sort pairs, I'll leave the time space thing, but it's going to change. And then we just choose the first pair, right? So we say, and then we'll figure out what the length is of the maximum thing that we can choose. So we'll grab pair 0. All right, and then this will just say that S is the pair, and then length is 1. Just doing it like this so it can be one line, because I'm an idiot. And then we look at each pair in pairs. So we'll look at each pair, start, end, in pairs. Okay? If we can choose it, what does that mean? Well, if the start time of this next pair in the system is sorted, right? If the start time of this next pair, so if the start time of this next pair is greater than the end time of our current pair, which is E, well, then we'll say, okay, SE and length equals SSEE and length plus 1. So now I'm just saying, okay, now this is the next thing we're going to choose. So now any future one has to meet this. And then at the end, length plus 1. And at the end, we just return length. All right, cool. So what's the runtime? Runtime's much better, right? Well, okay, so for time, now it's only O of n. O of n log n, sorry. Right, because we have to sort the system so that it's in terms of n time. That's going to take n log n time. And then we just do n operations, because we have to look at each n pairs. But then we just do a constant operation for each n pair, so that's only n. So it's n log n plus n. N log n is going to shadow n in the worst case after a while, right? For larger and larger cases of n. So that's n log n. For space, though, well, if we just assume that we're using heap sort, this is O of 1, right? Because I don't create, I create 2 variables here. No, okay, I create 3 variables here to keep information about the current pair that I'm looking at, and I swap that, but that doesn't grow with n, right? If n is 1,000,000, I'm still only going to create these 3 pairs, and this is constant space, right? If you use like in-place heap sort, but usually, this is going to be n space, so maybe that's something you should articulate to an interviewer, and that would actually be intelligent, right? Because they're going to understand, like, okay, this guy understands that there's different kinds of sorting algorithms, and different sorting algorithms can be constant space or they can be linear space, so it's good to understand that. All right, guys, so there's a dynamic programming approach, which I feel like is more intuitive. It's like longest increasing subsequence. And then there's a greedy approach, which seems more mathematical in nature. If you didn't get that, don't worry about it too much. This is a common problem, which is like greedily choosing tasks, which I learned about in college in an algorithms class, and I didn't understand it then, and I barely understand it now. Okay,